Newton's second law states that the mass of a body, times the acceleration vector of the body, is equal to the vector sum of all forces acting on the body. Newton's second law is valid for a body. But part of a body is also a body. Therefore Newton's second law is valid for part of a body too. We can reduce the part of the body that we are applying Newton's second law to, until it becomes infinitesimally small. In the limit when the volume of the body approaches zero, the mass of the body also approaches zero. Note that the volume can approach zero if any dimension of the volume approaches zero. So, a surface of zero thickness has a volume of zero, and therefore its mass is equal to zero. A line curve of zero thickness also has a volume and mass of zero. And a point of zero size also has a volume and mass of zero. We can write Newton's second law for a body of zero volume, which can be a surface, a line, or a point, as 0 times acceleration of the body is equal to the sum of the forces acting on the body. This means that the sum of the forces acting on a body of zero volume is equal to zero. This is Newton's third law of motion. Formally, Newton's third law is stated as: to every action on a body, there is an equal and opposite reaction. Note that Newton used the word action to mean force. Therefore, Newton's third law can also be stated as: to every force on a body, there is an equal and opposite reaction force. Since, to every force there is an opposite reaction force, then, the sum of an action, or force, and the reaction force are zero. Therefore, the sum of all action forces and reaction forces are zero. In other words, the sum of the forces is zero. Therefore, Newton's third law is actually a special case of Newton's second law. Newton's third law states that when the size of the body on which the forces are acting is zero, i.e. the body becomes a surface, a line or a point, then the sum of the forces acting on that surface, line or point is zero. For that to be true, if there is a force acting on that body, then there must be an equal and opposite reaction force that cancels out that force, such that the sum of the two forces is zero. So, we can think of Newton's third law as a special case of Newton's second law. Consider a body of mass m being suspended vertically using a rope of negligible mass. Let's look at a cross-section of the rope. The cross-section is a surface of zero thickness. Therefore it has a volume equal to zero. From Newton's third law, we know that the sum of the forces on this cross-section is equal to zero. We know that the body is pulling down on the bottom side of the cross-section, with a force equal to mass of the body times g. Since the sum of the forces on the cross-section must be zero, then, there must be an equal and opposite force acting on the cross-section. We denote this reaction force by F rope. F rope is equal in magnitude to Fg but acting in the opposite direction. F rope is pulling the body up, such that the body stays in equilibrium. Any cross-section of the rope is being pulled down by a force equal to the mass of the block times g. And at the same time, the cross-section is exerting an equal and opposite reaction force, F rope. So what is the origin of the rope reaction force? This reaction force is in fact caused by the rope intermolecular forces. The rope is composed of molecules that are being held together by intermolecular attracting forces. If we look at a cross-section of the rope on a molecular level, the molecules on the bottom cross-section are being pulled down by the block. But the molecules of the top cross-section are attracted to the top molecules. You can think of the attraction force between the top and bottom molecules as springs, connecting the top and bottom molecules. The springs in that cross-section get stretched, and so they produce a force that pulls the molecules back together. This force is the reaction force. Consider a block resting on a table. If we look at the contact surface between the block and the table, this contact surface has zero thickness, and therefore can be thought of as a body of zero volume. We know that the body is pushing down on the table with a force equal to mass of the body times g. From Newton's third law, we know that the sum of the forces on the contact surface must be zero. Then, the table must be exerting an equal and opposite force on the block. This equal and opposite force pushes the block up, such that the block stays in equilibrium. In order to understand the origin of the reaction force, we need to look on a molecular level at the contact area between the block and the table. The molecules on the surface of the block are exerting a force on the molecules on the surface of the table, equal to the mass of the block times g. This force is making the two surfaces come closer together. The intermolecular forces between the molecules on the surface of the table and the surface of the block are repelling back the two surfaces. We can think of the intermolecular forces as springs between the molecules on the two surfaces. The springs in that contact surface get compressed, and so they produce a force that pushes the molecules apart. This force is the reaction force.